How's it going, Adam?
Oh, okay. Did you guys work on the E&M homework last night? I like started it later and I was just like, oh, that's tough. And
Matrices. Who cares about matrices? So there are two contexts in which we have to deal with them all the time in research, engineering, and physics. One is what one could call operators. And the other one is what could call, data, but measurements. So operators are beloved by theorists because the mathematics that goes along is very beautiful and geometry is very intuitive. So the idea of the operators is that I have a state of a system, and the state of the system in introductory courses is, three. It's a pendulum, and there are 3 or 6 or some number of very few coordinates. And in real life, it's always a huge number. So state of the system could be weather in Chicago. The idea is, I tell you today it's cold, it's wet, etc. I give you 1,000 numbers and you look up your Newton, Navier-Stokes, and other laws of nature, and you perform a calculation and you operate, you do something, and you say, well, at time t, you'll be here. So this is the way of thinking goes to operators. So what it does is I am someplace in some state, and then sometime later, I'm still in the same realm of possibilities in the same state space, sometimes called phase space in mechanics and physics. And simplest version of it, I can explain by things like Hooke's laws or some very simple linear laws. Or I can, have actuary tables or some simple boring thing. And lots of thinking, especially by people who are not very sophisticated, is linear. So that's described as square matrices. And what it does is a typical question you want to answer is, if I'm within some little hyperbox in that space, so typical question. I have to compute where do I end up sometime later, and the linear operations change hyperboxes in parallelepipeds. And I typically have to do 2 things. One, that I'll do today, the hypercube gets deformed, and there is a natural set of coordinates to the parallelepiped, which its edges, and they're called eigenvalues and eigenvectors. So that's why we teach, about eigenvalues, eigenvectors, which I'll do today. And that's totally essential in much of engineering. I'll try to explain why it's not just linear problems. All problems in which you operate on something and there is a result, and you have to understand it. Now, physics and science, and there is no physics, engineering, Earth and atmospheric sciences anymore. It's a totally diffuse thing on Georgia Tech campus, who does what and who works on what problem, because methodology is similar, but problems are huge, different. And the most modern thing that one wants to understand in this millennium is brain. it's infinitely more interesting than, let's say, turbulence, which we don't understand, but we have inherited for the last 150 years as a problem. And what do they do in brain science? Well, they take a person or a monkey, they stick, let's say 100 electrodes, and they collect data, and data looks like this. This is time. This is neurons, or oranges or something. But the essential thing is it's very different from acting on state spaces. You are comparing time units to voltage measured on an area of your brain. And there is a finite number of these measurements you can do always. So let's say it's 1, 2, 98 of them. So that's your data. And what does the data looks like? At every instant of measurement, you read off the voltage on all of these guys. And that's an array of numbers, maybe to 3 digits of precision. Result is a rectangular matrix whose one side is the number of neurons, the other side is time. And typically what happens, number of neurons is 100. That doesn't change during your experiments. The time runs for as long as you believe you have a same state of the system you're measuring. They can be thousands or hundreds of thousands. So typical data that people in, let's say, physics or living systems or computational neuroscience have to deal with is a rectangular matrix. Now, what do they care about? It would be nice if it was just little pendula and we could write the law of motion and predict the state of the brain, but this is obviously not the intelligent way to think about it. They want to analyze what are the important features in neuronal activity over the time, and they do it in the following way. They have this big array. Now, some areas are almost dead, nothing happens. Some are big, there's some neurons have gone bananas because you have shown monkey or banana. So they care about big values of this rectangular matrix with 2 indices. When you teach these matrices, it's totally different. It's not operators. What you care about is if you look just at the world of neurons, so on the vertical axis, you're trying to find out important regions and what happens, who gets activated after whom. A hypercube, which is, n times n. So there is a part of this which is a square matrix, which has to do with neurons. You can also ask yourself, what is this thing doing in time? Well, there's an important part, t times t, and you care about time correlations. You care about if this happened, if something else happened sometime later. I might or might not do this. I will try to do this. I'll definitely do this stuff because, it's easy and we know it.
I actually had a question about the homework. I see the problems, but I see the numbers, but I don't see the actual questions themselves. Where can we find those?
Yeah, when you look at PDF, PDF is hyperlinked. So you click on the little red color and it goes to the end of the file and exercises at the end of the file.
Okay, thank you.
So whenever you see a color in your PDF, it either goes to the web. Okay, so matrices, 2 kinds, operators or data. number one. Number two, we do care about the determinants because they're totally essential to solve any problem in rocket science or any other science.